The rain did not stop for 2 million years. Not metaphorically, not in some geological approximation that scientists round off to make the numbers feel tidier. 2 million years, roughly the same span of time that separates us from the first members of the genus Homo who ever walked upright across the African savanna. For that entire stretch of deep time, water fell from the sky in quantities so staggering that entire mountain ranges were reshaped, entire ocean basins were refilled, and the very chemistry of the atmosphere was fundamentally altered. The Earth we live on today, its continents, its oceans, its breathable air, is in large part the direct consequence of that rain. This was not a storm in any sense the word carries today. A hurricane, even a Category 5, lasts a matter of days. The most persistent monsoon season on record stretches a few months. The mega-drought that gripped Western North America in recent decades, considered one of the most severe in 1,200 years, lasted roughly 2 decades. Now multiply that by 100,000. That is the scale of what geologists have named the Carnian pluvial episode, a period of sustained, planet-wide torrential rainfall that began approximately 232 million years ago during the Triassic period and fundamentally rewrote the conditions for life on Earth. The number itself is almost impossible to hold in the mind. 2 million years. Place it against a human lifespan of 80 years, and you are looking at 25,000 human lifetimes stacked end to end. If a single human generation had been alive at the start of this reign and somehow watched it without interruption, they would have needed to pass the vigil to their children, who passed it to their children, for 25,000 generations before the clouds finally began to break. Every civilization humanity has ever built, from the first Sumerian city-states to the present, fits inside a window of time roughly 6,000 years long. The Carnian pluvial episode lasted more than 300 times that entire civilizational history. What could cause something like that? The answer begins not with water, but with fire. Around 232 million years ago, in the region of what is now Western Canada and Alaska, one of the largest volcanic events in Earth's history began to unfold. The Wrangellia Large Igneous Province, a term that sounds bureaucratic, but describes something almost incomprehensible, erupted in pulses over millions of years, pouring basaltic lava across an area that geologists estimate exceeded 1 million square kilometers. To put that in perspective, 1 million square kilometers is larger than the combined land area of France, Germany, Spain, Italy, the United Kingdom, and Poland combined. That entire expanse was buried under layers of volcanic rock formed by lava flows that reached thicknesses of several kilometers. But the lava itself was not the primary driver of what came next. Volcanoes of this scale do not merely reshape the ground. They inject colossal quantities of gases into the atmosphere: carbon dioxide, sulfur dioxide, water vapor. The Wrangellia eruptions released so much carbon dioxide over their active phases that global temperatures rose significantly. Estimates from geochemical proxies, chemical signatures preserved in ancient rock formations, suggest that mean global temperatures during the peak of this warming event may have climbed by somewhere between 3 and 10 degrees Celsius above the already warm Triassic baseline. 3 to 10 degrees. That range might sound modest. It is not. The difference between the peak of the last ice age, when glaciers covered much of North America and northern Europe, and sea levels were roughly 120 meters lower than today, and the present climate is approximately 4 to 5 degrees Celsius. The Wrangellia-driven warming was potentially comparable in magnitude to that entire glacial to interglacial shift, but in the opposite direction, and starting from a world that was already warmer than our own. In a warmer atmosphere, the hydrological cycle accelerates. Warmer air holds more water vapor. For every degree Celsius of warming, the atmosphere's capacity for water vapor increases by roughly 7%. A relationship described by the Clausius-Clapeyron equation, one of the foundational relationships in atmospheric thermodynamics. More water vapor means more clouds. More clouds means more rain. And in the Triassic world, with volcanic forcing pushing temperatures steadily upward and the supercontinent Pangaea, then still largely intact, positioned in ways that concentrated moisture in specific regions, the rain came in quantities that have no modern equivalent. The geological record of the Carnian pluvial episode is written in rock. Sedimentary sequences from what is now Europe, North Africa, and parts of Asia show a dramatic shift during this period. From the red, oxidized, arid deposits characteristic of dry continental interiors to dark, organic-rich layers interspersed with evidence of flooding, river systems, and standing water. The red beds, geologists call them, rust-colored sandstones and mudstones that form in environments where iron in the sediment oxidizes freely, which only happens in the absence of sustained moisture. Then those red beds simply stop, replaced by something entirely different. The rock itself is the record. It does not speculate. It does not estimate. It simply preserves 232 million years of atmospheric chemistry in layers of stone. There is a persistent misconception worth addressing directly here, that extreme prolonged rainfall events are primarily features of ice ages, driven by the melting of glaciers or the reorganization of ocean circulation patterns associated with cold climates. The Carnian pluvial episode dismantles that assumption completely. The Triassic was not a cold world. There were no polar ice caps of any significance. The planet's mean surface temperature was substantially higher than today. The rain came precisely because of warmth, because heat energized the evaporative engine of the ocean, loaded the atmosphere with moisture, and drove weather systems of an intensity that modern meteorology has no direct frame of reference for. The Triassic world into which this rain fell was already a strange place by any modern standard. Pangaea was in the final stages of its long, slow fragmentation, though the major rifts that would eventually separate the continents into their present configurations were only beginning to open. The Tethys Sea, a vast equatorial ocean that no longer exists in any recognizable form, divided the northern landmass of Laurasia from the southern landmass of Gondwana, and its warm, shallow waters were a primary source of the moisture that the Wrangellia eruption's heat would eventually wring out of the sky. Life in this world was recovering, painfully and slowly, from the worst mass extinction in the history of complex animal life. The Permian-Triassic extinction event, approximately 52 million years earlier, which had eliminated something between 90 and 96% of all marine species and roughly 70% of terrestrial vertebrate species. Recovery had been underway for tens of millions of years. New groups of animals had begun to diversify. Early archosaurs, the lineage that would eventually give rise to both dinosaurs and crocodilians, were establishing themselves. Early relatives of the turtles had appeared. The first true flies, belonging to the order Diptera, had evolved. Ecosystems were rebuilding themselves in the slow, opportunistic way that evolution always does after catastrophe. And then the rain began. What it did to those recovering ecosystems, to the animals, the plants, the soil chemistry, the ocean chemistry, is a story written in extinction data, in isotope ratios, in the morphology of pollen grains preserved in ancient lake sediments. The Carnian pluvial episode was not a gentle, nourishing rain, it was a global disruption. And in the chaos it created, something remarkable happened, something that would set the trajectory of complex life on Earth for the next 200 million years. That story begins with what the rain destroyed, and what it left behind when it finally stopped. Geologists do not find the Carnian pluvial episode in a single location. They find it everywhere. From the Dolomite formations of the Italian Alps to the desert sediments of Tunisia, from the ancient lake beds of Central Europe to the marine sequences preserved in the mountains of what is now Iran, from the floodplain deposits of Argentina to the coastal sediments of eastern Greenland. The same signal, written in rock on every major landmass that existed during the Triassic period, all pointing to the same window of time, roughly 232 to 234 million years ago. A global event leaves a global fingerprint, and the Carnian pluvial episode left one of the most legible fingerprints in the entire Mesozoic geological record. The discipline that reconstructed this event is called chemostratigraphy, the reading of chemical signals embedded in ancient rock layers to reconstruct past environmental conditions. It is painstaking, methodical work. A geologist extracts a core sample from a sedimentary sequence, slices it into sections representing individual time intervals, and then subjects those sections to a battery of isotopic analyses. Carbon isotopes, oxygen isotopes, strontium isotopes. Each element, each ratio, encodes a different piece of environmental information, like separate instruments in an orchestra that together produce a coherent account of a vanished world. The carbon isotope record from Carnian age sediments tells a specific story. Carbon exists in two stable forms, carbon-12 and carbon-13. Volcanic activity releases carbon dioxide enriched in carbon-12, lighter, more common, produced in abundance by the degassing of mantle-derived magmas. When large volcanic provinces erupt over extended periods, they shift the ratio of carbon-12 to carbon-13 in the ocean and atmosphere measurably. The Carnian record shows exactly this shift in multiple locations across the globe, at precisely the time interval corresponding to the peak Rangelia volcanic activity. The chemistry of the rock and the timing of the eruptions align with a precision that eliminates coincidence as an explanation. The oxygen isotope record adds a second layer. Oxygen-18 and oxygen-16 behave differently depending on temperature and the water cycle. In warmer, wetter conditions, the ratio of oxygen isotopes in carbonate sediments, the calcium carbonate shells of ancient marine organisms preserved in limestone, shifts in predictable ways. The Carnian carbonate record shows those shifts. Temperature proxies derived from oxygen isotopes in Carnian age marine fossils suggest a warming event of significant magnitude, consistent with the carbon dioxide forcing implied by the volcanic record. The two signals are not independent. They are two different chemical languages describing the same physical reality. What were the actual conditions on the ground, or rather, under the rain? The sedimentological record gives the most direct answer. In the Germanic Basin, a broad, shallow marine and coastal region that covered much of what is now Central Europe during the Triassic, geologists have documented one of the clearest stratigraphic records of the Carnian transition. Below the Carnian boundary, the sediments are dominated by evaporites, gypsum, anhydrite, halite, the chemical precipitates that form when water evaporates in arid, hypersaline environments. Evaporites are unambiguous climate indicators. They do not form in humid conditions. They require sustained aridity, high temperatures, and low precipitation. The Germanic Basin evaporate sequence represents millions of years of consistently dry conditions during the early and middle Triassic. Then, at the Carnian horizon, the evaporates stop. They are replaced by sequences of sandstone, shale, and mudstone, characteristic of fluvial and lacustrine environments, rivers, floodplains, lakes. Coarse-grained sediments that were transported by moving water and deposited when flow velocity decreased. Fine-grained clays that settled out of suspension in standing water bodies. Organic rich dark layers indicating the accumulation of plant material in waterlogged soils. The transition is not gradual in the way that geological transitions are often imagined. In the context of deep time, it is abrupt, occurring within a stratigraphic interval representing perhaps a few tens of thousands of years, a geological eye blink. The pollen record amplifies this picture in remarkable detail. Palynology, the study of ancient pollen and spores preserved in sediment, provides a high-resolution window into past vegetation, and vegetation is one of the most sensitive indicators of climate. Dry-adapted plant communities produce characteristic pollen assemblages. Humid-adapted communities produce different ones. The Carnian pollen record across multiple European and Gondwanan sections shows a clear and dramatic shift. Arid-adapted gymnosperms and drought-tolerant flora declining, replaced by fern communities and moisture-requiring plants that thrive in wet, disturbed environments. Ferns, specifically, are worth pausing on. In the post-extinction and post-disturbance geological record, fern spikes are a recurring signal. After the Cretaceous-Paleogene impact event 66 million years ago, the one that ended the non-avian dinosaurs, fern spores dominate the immediate post-impact sediment layers globally. Ferns are opportunists. They colonize disturbed, wet, open ground faster than almost any other vascular plant group. Their appearance in abundance in the Carnian record is not coincidental. It is a biological response to exactly the kind of environmental disruption, widespread flooding, soil disturbance, destruction of established plant communities, that sustained heavy rainfall on a continental scale would produce. The marine record of the Carnian pluvial episode is equally striking, though it records a different dimension of the same event. The ocean is not a passive recipient of climate change. It is an active participant. Sustained heavy rainfall over continental land masses increases the flux of fresh water and dissolved terrestrial material into coastal marine environments through river systems. This freshwater influx, geologists call it a positive hydrological anomaly, reduces surface salinity in shallow coastal seas, alters ocean stratification, and delivers elevated concentrations of terrestrial nutrients and organic carbon to marine ecosystems. The Carnian marine record shows evidence of all of these effects. Carbonate production, the building of calcium carbonate shells and reefs by marine organisms, declined significantly during the Carnian wet phase in multiple shallow marine sections. Reef-building communities, which require clear, oligotrophic, nutrient-poor waters and stable salinity conditions, are particularly sensitive to freshwater influx and elevated terrestrial nutrient loading. The major Triassic reef-building organisms, primarily sponge microbial reef communities that had been rebuilding after the Permian-Triassic extinction, suffered severe disruption during the Carnian wet episode. Their recovery afterward would take millions of years. Anoxic events, episodes of oxygen depletion in bottom waters, are recorded in some Carnian marine sequences as well. When heavy rainfall delivers large quantities of organic material to coastal seas, microbial decomposition of that material consumes dissolved oxygen, creating dead zones where complex animal life cannot survive. Modern analogs exist in the Gulf of Mexico, where nutrient runoff from the Mississippi River watershed creates a seasonal hypoxic zone covering thousands of square kilometers. The Carnian version of this process operated on a planetary scale, for a duration measured not in seasons, but in geological time intervals. A misconception that surfaces repeatedly in popular accounts of this event deserves direct correction. The Carnian pluvial episode is sometimes described as though it were essentially a prolonged version of a modern monsoon, an intensification of the seasonal wet-dry cycles that govern precipitation in tropical and subtropical regions today. This framing fundamentally misrepresents the mechanism and the magnitude. Modern monsoon systems are driven by seasonal differential heating between continental land masses and adjacent ocean surfaces, operating within an atmospheric system that has been in broadly similar configuration for millions of years. The Carnian event was driven by a forcing mechanism of an entirely different order. Sustained volcanic injection of carbon dioxide into the atmosphere over timescales of millions of years, operating on a continental configuration, Pangaea and the Tethys Sea, that has no modern equivalent. The analogy to a monsoon is like comparing a garden hose to a burst dam. The duration matters in ways that go beyond simple arithmetic. 2 million years of elevated rainfall does not merely deliver more water than 2,000 years of elevated rainfall. It fundamentally restructures landscapes. River systems that drain continents carve new valleys, transport enormous quantities of sediment to coastal margins, and build deltaic systems that alter coastlines. Soil chemistry transforms as sustained leaching removes soluble minerals and fundamentally changes the substrate available for plant life. The weathering of silicate rocks, a process that consumes atmospheric carbon dioxide as rocks react with carbonic acid in rainwater, accelerates dramatically under sustained high precipitation conditions, creating a slow negative feedback on the volcanic carbon dioxide, forcing that would eventually help draw the wet phase to a close. This is where the story begins to turn. Because embedded within the Carnian record, in the sediments, the isotopes, the fossils, there is evidence of something more than destruction. The disruption of established ecosystems, the restructuring of landscapes, the opening of new ecological opportunities in waterlogged, disturbed, nutrient-rich environments, these were not simply damaging. They were generative. The conditions created by 2 million years of planetary-scale rainfall were precisely the conditions under which certain lineages of animals, lineages that had been marginal, opportunistic, ecologically minor, began to do something extraordinary. The question is what those lineages were, and why the rain of all things gave them their opening. Water is the most ordinary substance on Earth. It covers 71% of the planet's surface. It falls from the sky in every inhabited region of the world. It is so familiar, so constantly present, that the human mind struggles to treat it as anything remarkable. That familiarity is precisely what makes the Carnian pluvial episode so difficult to conceptualize, because the event was not driven by an exotic alien force. It was driven by water, by rain, by the same molecular compound that fills every ocean, every cloud, every living cell. The difference was the scale of the engine producing it and the duration over which that engine ran without interruption. The hydrological cycle, the continuous movement of water between the ocean surface, the atmosphere, and the land, is ultimately a heat engine. It runs on solar energy and the thermodynamic properties of water as a molecule. Water at the ocean surface absorbs solar radiation, gains kinetic energy, and transitions from liquid to vapor, a process called evaporation. That vapor rises into the atmosphere, cools as it ascends, and condenses around microscopic aerosol particles, dust, sea salt, volcanic ash, to form cloud droplets. When enough droplets aggregate, precipitation falls. The water returns to the ocean through rivers and groundwater flow, and the cycle begins again. The rate at which this cycle operates is directly governed by temperature. Specifically, it is governed by a relationship described by the Clausius-Clapeyron equation, derived independently by Rudolf Clausius and Benoit-Paul-Émile Clapeyron in the 19th century. The equation describes the relationship between temperature and the saturation vapor pressure of water, essentially, how much water vapor the atmosphere can hold at a given temperature. The relationship is exponential, not linear. For every 1 degree Celsius increase in atmospheric temperature, the saturation vapor pressure increases by approximately 6 to 7%. This means a warmer atmosphere does not merely hold slightly more water. It holds dramatically more water, with the capacity scaling upward steeply as temperatures rise. During the Carnian pluvial episode, the Rangelia volcanic system had been injecting carbon dioxide into the atmosphere for hundreds of thousands of years before the wet phase peaked. Carbon dioxide is a greenhouse gas. It absorbs outgoing infrared radiation from the Earth's surface and re-radiates a portion of it back downward, reducing the rate at which the planet loses heat to space. This is not a hypothesis or a model prediction. It is a direct consequence of the molecular structure of carbon dioxide, which has vibrational modes that interact with infrared photons at specific wavelengths. The physics operates the same way regardless of geological epoch. The global mean surface temperature during the Triassic was already substantially elevated compared to the present. Proxy data from oxygen isotopes in Triassic marine carbonates suggest mean global temperatures somewhere between 4 and 8 degrees Celsius, warmer than the pre-industrial baseline. There were no significant polar ice caps. The equator-to-pole temperature gradient was shallower than today, meaning heat was distributed more evenly across the planet's surface. Into this already warm system, the Rangelia eruptions injected additional carbon dioxide, pushing temperatures higher still. The atmosphere's water vapor carrying capacity rose in lockstep. And the ocean, covering a vast surface area in the Tethyan realm and the Panthalassic Ocean that surrounded Pangaea, responded by evaporating at an accelerated rate. The Panthalassic Ocean is worth pausing on because it is a body of water with no modern analog. During the Triassic, it covered roughly half of the entire planet's surface, a single, continuous ocean of enormous extent, stretching from pole to pole and from the eastern coast of Pangaea to the western coast. Its surface area dwarfed any individual ocean basin that exists today. The Pacific Ocean, the largest modern ocean, covers approximately 165 million square kilometers. The Panthalassic Ocean covered considerably more. When a warm Triassic atmosphere accelerated evaporation from that surface, the volume of water vapor entering the global atmospheric circulation was immense. The configuration of Pangaea itself shaped where that moisture went. The supercontinent was oriented roughly north-south, straddling the equator, with the Tethys Sea forming a broad equatorial embayment on its eastern side. The intertropical convergence zone, the band of rising warm air and heavy precipitation near the equator that drives the world's most intense rainfall systems today, operated in the Triassic as it does now, but its interaction with the unique Pangaean coastline geometry and the vast interior continental regions created precipitation patterns that modern climate models are only beginning to reconstruct with confidence. The continental interior of Pangaea presents a particular challenge. Today, the interiors of large continents, Central Asia, the interior of North America, Central Australia, are characteristically arid because moisture from ocean evaporation is precipitated out before it can penetrate far inland. The Triassic continental interior had faced the same dynamics for tens of millions of years, producing the red bed evaporate sequences that dominate the early and middle Triassic record. The Carnian transition required something powerful enough to breach that continental aridity barrier, to drive moisture deep into land masses that had been dry for geological epochs. The mechanism was almost certainly a combination of factors. Elevated sea surface temperatures in the Tethys and Panthalassic oceans increased the energy content of moisture-laden air masses moving onshore. The warming of the continental interior itself reduced the thermodynamic barrier to moisture penetration by weakening the stable subsidence that normally suppresses precipitation over dry continental regions. And the increased water vapor content of the atmosphere meant that when precipitation did occur, it was more intense. Individual rainfall events delivering larger quantities of water per unit time than would occur in a cooler, drier atmospheric state. Intense rainfall on geological timescales does something to rock that slow, moderate rainfall does not. It accelerates chemical weathering at a dramatic rate. The primary weathering reaction relevant here involves carbonic acid, a weak acid formed when carbon dioxide dissolves in rainwater, reacting with silicate minerals in exposed rock surfaces. The reaction consumes atmospheric carbon dioxide and produces dissolved bicarbonate ions that are carried by rivers to the ocean, where they eventually precipitate as calcium carbonate in sediments. This process, known as the silicate weathering negative feedback, is one of the primary long-term regulators of atmospheric carbon dioxide concentration on geological timescales. The rate of silicate weathering scales with both temperature and precipitation. More rain, falling more intensely, moving across a continental surface with greater frequency and volume, accelerates the consumption of atmospheric carbon dioxide by orders of magnitude compared to arid baseline conditions. This is one of the reasons geochemists believe the Carnian wet phase eventually moderated and ended. The volcanic forcing that initiated it gradually declined as the Rangelia eruptions waned, while simultaneously the enhanced weathering driven by the rainfall itself began drawing down the excess carbon dioxide that had fueled the warming. The planet's own chemistry acted as a thermostat, imprecise, slow, operating on timescales of hundreds of thousands to millions of years, but real. The soils of the Carnian world recorded this chemical transformation in ways that persist in the geological record today. Paleosols, ancient soil horizons preserved within sedimentary sequences, show a shift during the Carnian wet phase from calcic horizons, characteristic of arid and semi-arid soils where calcium carbonate accumulates near the surface, to deeply leached profiles with depleted upper horizons and accumulated clay minerals at depth. This pattern, called lessivage in soil science, requires sustained percolation of water through the soil column over extended periods. It cannot be produced by seasonal rainfall. It requires persistent, prolonged moisture penetration that systematically strips soluble minerals from the upper soil and transports them downward. The ancient soils are a slow-motion record of 2 million years of rain, written in clay mineralogy and iron depletion profiles. Simultaneously, the silicate weathering reactions liberated enormous quantities of dissolved nutrients, phosphorus, silica, calcium, magnesium, from continental rock surfaces and transported them via river systems to coastal marine environments. The ocean chemistry of the Carnian changed as a direct consequence. Elevated dissolved silica favored certain groups of siliceous marine organisms, radiolarians, siliceous sponges, whose abundance and preservation in Carnian marine sediments increases markedly during the wet phase. The pulse of terrestrial nutrients to coastal seas created conditions of elevated productivity in some regions and oxygen depletion in others, reshaping marine ecological communities in ways that the fossil record preserves with surprising clarity. All of this, the isotope signals, the sediment sequences, the paleosol profiles, the marine geochemistry, converges on a single coherent picture. Not of an event imposed from outside the Earth system, not of an asteroid or a gamma-ray burst or an external cosmic catastrophe, but of the planet's own internal systems interacting in ways that temporarily overwhelmed the equilibria that normally govern surface conditions. the Earth tipping for 2 million years out of one stable state and into another. What lived through that tipping, and what did not, was not determined by size or speed or intelligence. It was determined by one thing above all others: flexibility. The ability to exploit conditions that no ecosystem on Earth had experienced in the preceding tens of millions of years. And among the creatures navigating a world of endless rain and restructured landscapes, one group was about to demonstrate a flexibility so extreme that its consequences are still visible today. In every bird that flies, in every crocodile that waits at a riverbank, in every lizard that basks on a warm rock. The dinosaurs were about to find their moment. In 1986, a paleontologist named Michael Benton published a paper that reframed a question scientists had been asking for decades. The question was deceptively simple. Why did the dinosaurs rise to dominance? Not how they survived, not what physical adaptations they possessed, but why, in the competitive ecological landscape of the Triassic, they came to replace the other archosaur lineages that had, for tens of millions of years, occupied the dominant vertebrate niches on land. Benton's answer was not the one most paleontologists expected, and it pointed directly at the rain. The prevailing assumption before Benton's work was what biologists call competitive displacement. The dinosaurs in this model were simply better. Faster metabolisms, more efficient locomotion, superior predatory or herbivorous adaptations, some intrinsic biological advantage that allowed them to outcompete the crurotarsal archosaurs, the rhynchosaurs, the dicynodonts, and the other dominant Triassic vertebrate groups in direct ecological contest, gradually replacing them across millions of years of sustained competition. It was a satisfying narrative. Evolution as meritocracy. The best design wins. The fossil record does not support it. What the fossil record shows instead is an abrupt, non-gradual transition. The dominant Triassic vertebrate groups, particularly the etosaurs, the ornithosuchids, the large predatory rauisuchians that had occupied the apex predator niche across much of Pangaea, did not fade slowly as dinosaur diversity increased. They disappear from the record geologically suddenly, in a pattern consistent not with competitive displacement, but with extinction followed by ecological opportunity. The timing of their disappearance overlaps with a major biotic crisis that geologists and paleontologists now recognize as one of the significant extinction events of the Mesozoic, the Carnian crisis, occurring at precisely the boundary of the Carnian pluvial episode. The extinction data is preserved in the vertebrate fossil record of multiple continents. In the Santa Maria and Ishigualasto formations of South America, among the most productive Triassic vertebrate fossil sites in the world, the faunal turnover at the Carnian boundary is documented in exceptional detail. Below the boundary, the fauna is dominated by rhynchosaurs, barrel-bodied, beaked herbivores that were among the most abundant large terrestrial vertebrates of the Middle Triassic, potentially accounting for more than 40% of individual vertebrate specimens in some fossil assemblages. They were, by any measure, ecologically successful animals. They had diversified across Gondwana, evolved multiple body forms, and sustained large populations for millions of years. After the Carnian boundary, they are essentially gone. Not reduced, not marginalized. Gone, replaced in the fossil record by a fundamentally different fauna in which dinosauriform archosaurs are dramatically more prominent. The transition in the Ishigualasto Formation, one of the most precisely dated Triassic sections in the world, using uranium-lead radiometric dating of volcanic ash layers interbedded with the fossil-bearing sediments, occurs within a stratigraphic interval that represents a geologically brief window of time. The rhynchosaurs do not gradually decline across millions of years of strata. Their abundance collapses. What drove the collapse? The answer requires understanding what rhynchosaurs ate and how they were adapted to eat it. Rhynchosaurs were almost certainly specialized feeders on seed ferns, Triassic plants belonging to groups like the Dicroidium flora that dominated Gondwanan vegetation for tens of millions of years. Their beaked jaws and complex dental batteries were adapted for processing the tough seeds and fibrous stems of these plants with an efficiency that other Triassic herbivores could not match. The Dicroidium flora was, for rhynchosaurs, both home and larder, a vast continent-spanning resource base that their entire evolutionary history had been shaped to exploit. The Carnian pluvial episode destroyed the dicroidium flora. The paleobotanical record from Gondwanan sections spanning the Carnian boundary shows the same transition that the vertebrate record does. The seed fern-dominated vegetation communities that had characterized Gondwana through the Middle Triassic declining sharply and being replaced by fern-dominated and conifer-dominated communities adapted to the wetter, more disturbed conditions of the Carnian wet phase. The specific plants that rhynchosaurs had evolved to eat were disappearing, replaced by vegetation types their anatomy was not equipped to process efficiently. Without the food base, the rhynchosaurs collapsed. And when the rhynchosaurs collapsed, the herbivore niche they had dominated, one of the most ecologically important niches in any terrestrial ecosystem, was suddenly open. The dinosaurs that moved into that vacancy were not, at the time, the giants of popular imagination. The earliest definitive dinosaurs, forms like Eoraptor lunensis and Eodromaeus murphy from the Ischigualasto Formation and Herrerasaurus ischigualastensis from the same unit, were modest-sized bipedal, predominantly carnivorous or omnivorous animals. Eoraptor was roughly the size of a large dog. Herrerasaurus was larger, perhaps 3 to 4 meters in length, but still dwarfed by the Rauisuchian archosaurs that had been apex predators earlier in the Triassic. These were not animals that dominated their ecosystems through physical superiority. They were animals present at the right moment, in a landscape that had just lost many of its previous occupants. The diversification that followed was rapid by evolutionary standards. Within a few million years of the Carnian extinction pulse, dinosaurian body plans were diversifying across multiple lineages, sauropodomorphs developing the elongated necks and large body sizes that would eventually produce the largest terrestrial animals in Earth's history, ornithischians beginning the evolutionary experiments that would lead to the armored, horned, and duck-billed dinosaurs of the Cretaceous, theropods expanding into both small agile predator and large apex predator niches. The ecological space cleared by the Carnian extinctions was not filled cautiously, it was filled explosively. The marine realm recorded its own version of the same turnaround. The disruption of Triassic reef ecosystems by the Carnian wet phase, the carbonate crisis, the influx of terrestrial nutrients, the episodes of anoxia in shallow seas, had decimated the sponge microbial reef communities that dominated Triassic shallow marine environments. After the wet phase ended and ocean conditions stabilized, the organisms that moved into the vacated reef-building niche were not the same groups that had previously occupied it. Scleractinian corals, the group that builds all modern coral reefs, had first appeared in the fossil record earlier in the Triassic, but had remained ecologically marginal while the sponge microbial system dominated. After the Carnian disruption, Scleractinian corals diversified rapidly into the vacated reef-building niche and established the ecological dominance they retain to the present day. Every coral reef on Earth today, the Great Barrier Reef, the reefs of the Caribbean, the atolls of the Pacific, exists because the Carnian pluvial episode cleared the ecological space that allowed Scleractinian corals to rise. The same pattern extends to other marine groups. Ichthyosaurs, marine reptiles that had diversified extensively in the earlier Triassic, underwent significant faunal turnover around the Carnian boundary. Several previously dominant ichthyosaur lineages disappear from the record at this interval, replaced by forms that would persist into the Jurassic. The first plesiosaurs, long-necked marine reptiles that would become iconic Mesozoic marine predators, appear in the fossil record in the Norian stage immediately following the Carnian, suggesting their radiation was facilitated by the ecological openings created by the Carnian extinctions. The pattern repeats across taxonomic groups and across both terrestrial and marine realms with a consistency that is difficult to attribute to coincidence. Mammal-like reptiles, the cynodonts and dicynodonts that had been major components of Triassic terrestrial faunas, were significantly reduced in both diversity and ecological dominance after the Carnian crisis. Early turtle lineages diversified. The first evidence of several insect orders appears in post-Carnian sediments. Even within the plant kingdom, the restructuring of vegetation communities during the wet phase had lasting consequences. The gymnosperm-dominated Gondwanan flora that emerged after the dicroidium collapse was a fundamentally different ecological system from what preceded it. The scientific community's recognition of the Carnian pluvial episode as a major driver of Mesozoic biodiversity is relatively recent. For much of the 20th century, the Triassic was treated as a single, broadly uniform interval of recovery following the Permian-Triassic extinction, with the rise of dinosaurs attributed to the end Triassic extinction event approximately 201 million years ago. A separate and better documented crisis caused by the eruption of the Central Atlantic Magmatic Province. The Carnian event was recognized in European geological literature for decades, primarily as a sedimentological phenomenon, but its biological consequences were not synthesized into a coherent picture until the accumulation of vertebrate fossil data from South America, the refinement of radiometric dating techniques, and the development of the chemostratigraphic tools that allowed the event to be correlated globally. Benton's 1983 and 1986 analyses of Triassic vertebrate diversity, combined with subsequent work by Massimo Bernardi, Piero Gianola, and their colleagues in the early 2020s using newly refined carbon isotope and sedimentological data, built the case incrementally. Each new dataset from a different continent, each new radiometric date from a volcanic ash layer in a Triassic fossil section, each new isotope record from a marine carbonate sequence added another line of evidence converging on the same conclusion. The rain did not merely alter the landscape, it reset the biosphere. 2 million years of altered ecology, collapsed food webs, vacant niches, and restructured vegetation communities had created a world in which the inherited hierarchies of the early and middle Triassic no longer applied. The animals that survived were not necessarily the strongest or the most complex. They were the ones whose biology happened to be compatible with a planet that had been fundamentally rearranged by water. What the rain built, it built from wreckage. And the most spectacular thing it built was only just beginning to reveal itself in the sediments of the late Triassic, in the footprints, the bones, the teeth, and the trackways of animals whose descendants would rule the Earth for 135 million years. The sediments do not lie, they never have. At a depth of roughly 232 million years in the geological column, across sections on 5 continents, the rock tells the same story with the precision of a chemical clock. The Carnian pluvial episode did not build gradually to its peak the way a tide rises, slow, predictable, reversible. The proxy records show a system that crossed a threshold. Carbon isotope excursions in marine carbonates shift sharply negative, indicating a massive injection of isotopically light carbon into the ocean atmosphere system. Oxygen isotope temperatures spike. The evaporate record vanishes. The red beds disappear. And the sedimentary architecture of entire continental basins transforms, within geologically brief intervals, from the signature of aridity into the signature of a world drowning in its own hydrological cycle. The peak of the Carnian wet phase, based on the convergence of carbon isotope data, palynological records, and vertebrate faunal turnover evidence, occurred approximately 232 million years ago. The duration of the most intense phase, the interval during which the isotope excursions are most pronounced and the sedimentological evidence for flooding is most pervasive, is estimated at somewhere between 1 and 2 million years, though the broader climatic disruption persisted longer as the system oscillated before stabilizing. 1 to 2 million years of peak intensity. The human mind keeps reaching for analogies and finding none adequate. The entirety of recorded human history, every war, every empire, every technological revolution from the first stone tools to the present, compresses into less than 1/10,000th of that interval. The atmospheric carbon dioxide concentrations during the peak Carnian warming are reconstructed from multiple independent proxies: the carbon isotope record in paleosols, the stomatal density of fossil plant leaves, which decreases as carbon dioxide rises because plants require fewer stomatal pores to absorb sufficient carbon dioxide from a richer atmosphere, and geochemical models constrained by the volcanic flux estimates from the Rangelia province. The reconstructed peak concentrations range from approximately 2,000 to 4,000 parts per million. The pre-industrial atmospheric concentration was approximately 280 parts per million. The peak Carnian atmosphere contained somewhere between 7 and 14 times as much carbon dioxide as the pre-industrial baseline. At those concentrations, the radiative forcing, the imbalance between incoming solar energy and outgoing infrared radiation, was substantial enough to sustain mean global temperatures significantly above anything in the modern instrumental record. What does a planet look like at 4,000 parts per million carbon dioxide, with no polar ice caps, a global ocean of enormous extent, and 2 million years of sustained volcanic degassing driving the system continuously warmer? The answer, reconstructed from proxy data, is striking in its coherence. Sea surface temperatures in the Tethys realm, the equatorial ocean between Laurasia and Gondwana, reached values estimated at 35 to 38 degrees Celsius in some shallow coastal regions. For context, the warmest sea surface temperatures recorded anywhere in the modern ocean, in the Persian Gulf during summer, reach approximately 35 degrees Celsius. The Carnian Tethys was, across its breadth and for sustained geological intervals, as warm as the hottest modern ocean on its hottest seasonal extreme, and it was evaporating accordingly. The water vapor feedback, the amplifying loop by which initial warming increases atmospheric water vapor, which itself is a greenhouse gas which produces additional warming, which produces additional water vapor, operated without the moderating influence of polar ice caps that, in the modern climate system, provide a stabilizing albedo feedback. Ice reflects solar radiation back to space. A planet without ice absorbs more solar energy at high latitudes, warming further. The Carnian world had no significant cryosphere to provide that stabilization. The feedback loops ran in one direction, reinforcing each other for hundreds of thousands of years. The rainfall that resulted was not distributed uniformly across the planet's surface. Climate model simulations of Triassic paleogeography, using the reconstructed positions of continents, ocean basins, and mountain ranges, indicate that the Tethyan coastal regions and the margins of Pangaea, adjacent to the Panthalassic Ocean, received the most intense precipitation. These were the regions where warm, moisture-laden oceanic air masses made landfall, rose orographically over coastal terrain, cooled, and precipitated. Annual rainfall totals in these regions during the peak Carnian wet phase may have exceeded modern tropical rainforest values by substantial margins. The Amazon basin today receives approximately 2,000 to 3,000 millimeters of precipitation annually. Some Carnian coastal regions may have received considerably more, sustained not for a single year or a decade, but for geological intervals. The geomorphological consequences were direct and measurable in the rock record. River systems draining the Carnian continental margins developed braided and meandering channel architectures characteristic of high discharge, high sediment load fluvial systems. Channel sandstone bodies in Carnian age fluvial sequences are thick, laterally extensive, and interbedded with fine-grained floodplain deposits on a scale that indicates river systems of enormous discharge, comparable to or exceeding the largest modern river systems on Earth. The Carnian rivers were not merely larger versions of their predecessors. They were categorically different systems, transporting sediment volumes and dissolved chemical loads that reshaped continental margins and built massive deltaic complexes along the shores of the Tethys and Panthalassic oceans. Delta systems built by major rivers are among the most productive and ecologically complex environments on Earth. The Nile Delta, the Ganges-Brahmaputra Delta, the Mississippi Delta, each represents a zone of intense ecological activity where freshwater, marine, and terrestrial ecosystems intersect. The Carnian deltas, built by river systems of far greater discharge draining a supercontinent in a hyperhumid climate, were vast. They delivered nutrients, organic carbon, and fresh water to coastal seas in quantities that restructured marine chemistry across entire ocean basins. The geochemical fingerprint of this terrestrial input is preserved in the carbon and sulfur isotope records of Carnian marine sediments. Elevated organic carbon burial, fluctuating sulfur isotope ratios reflecting cycles of marine anoxia and oxygenation, and shifts in strontium isotope ratios recording the enhanced weathering of continental silicate rocks. The strontium isotope record deserves particular attention because it is one of the most robust tracers of continental weathering intensity in the geological record. Strontium-87, produced by the radioactive decay of rubidium-87 in old continental crust, is delivered to the ocean by rivers at a rate that scales directly with the intensity of continental weathering. When weathering intensifies, as it does under conditions of elevated temperature and rainfall, the ratio of strontium-87 to strontium-86 in seawater rises. Triassic marine carbonates record a shift in this ratio across the Carnian interval that is consistent with a dramatic intensification of continental weathering flux, independent of and corroborating the sedimentological and palynological evidence. The chemical signal in the ocean reflects what the sediments on the continents show directly, a planet being chemically processed by water at an accelerated rate. The ecological consequences in the marine realm during the peak Carnian wet phase were severe and widespread. Carbonate platform systems, the shallow water carbonate-producing environments that build reefs and carbonate shelves, collapsed across the Tethyan domain. The crisis in carbonate production is documented in the stratigraphic record as the Carnian carbonate crisis, a term used in the geological literature to describe the widespread drowning or cessation of Triassic carbonate platforms during this interval. Carbonate platforms require clear, shallow, warm, oligotrophic water with stable salinity. The Carnian Ocean delivered the opposite: elevated turbidity from river sediment input, fluctuating salinity from freshwater influx, elevated nutrient concentrations driving algal blooms and oxygen depletion, and carbonate undersaturation in shallow waters driven by the influx of carbon dioxide from the atmosphere and by respiration of the large organic carbon loads delivered from land. The terrestrial biosphere at the peak of the wet phase was a system in active reorganization. The vegetation communities of the Gondwanan and Laurasian landmasses were not static during the Carnian. They were tracking the changing climate in real time, with the fast-responding fern and early gymnosperm communities expanding into disturbed, waterlogged terrain as the slower-growing, drought-adapted flora of the Middle Triassic retreated or collapsed. Soil formation processes were fundamentally altered. The lateritic and deeply weathered soil profiles developing under sustained high precipitation conditions were stripping nutrients from upper soil horizons and concentrating them in deep leaching zones, creating substrate conditions that favored certain plant communities over others in a self-reinforcing cycle. The dinosaurs navigating this world were doing so as ecological opportunists in the truest sense. Their relatively small body sizes in the early radiation, their apparent dietary flexibility, the dentition evidence from early dinosauriform fossils suggests both carnivorous and omnivorous feeding strategies, and their bipedal locomotion, which may have been advantageous for moving through waterlogged, structurally complex terrain, positioned them well for a world in which established ecological hierarchies had been disrupted. They were not the largest animals in their ecosystems. They were not the apex predators. But they were present, they were diversifying, and the world was clearing space for them with every year of rain. The rain was the catastrophe, and the catastrophe was the opportunity. 2 million years of it. 2 million years of chemical weathering, of flooded landscapes, of collapsed food webs and vacated ecological niches, of ocean chemistry pushed to extremes, and then gradually, incrementally, pulled back toward equilibrium by the same geological processes that had destabilized it. The Rangelia eruptions waned, the volcanic carbon dioxide input declined. The accelerated silicate weathering, driven by the rain itself, consumed excess atmospheric carbon dioxide at an enhanced rate. Temperatures fell. The hydrological cycle moderated. The red beds returned eventually to the sedimentary record, though the world they were deposited in was not the world that had preceded the rain. It was a fundamentally different biosphere, with different dominant organisms, different ecological structures, different reef builders, different apex predators. The planet had passed through itself. And what emerged on the other side was the Mesozoic world. The world of dinosaurs, of scleractinian reefs, of the first mammals scurrying through undergrowth, of flying reptiles riding thermals above landscapes that 2 million years of rain had carved, leached, and rebuilt from the ground up. The clouds broke. Eventually, they always do. The precise timing of the end of the Carnian pluvial episode is constrained by the same geochemical tools that identified its onset. Carbon isotope values in marine carbonates return toward baseline. Oxygen isotope temperature proxies decline, indicating cooling. The strontium isotope ratio in seawater, which had risen through the peak wet phase as enhanced continental weathering delivered isotopically radiogenic strontium to the ocean, begins to level off and gradually decrease as weathering intensity moderates with the cooling and drying climate. The red beds return to continental sedimentary sequences, not immediately, not everywhere at once, but progressively, section by section, across the Nourian stage that follows the Carnian. The planet's hydrological cycle decelerated. The engine, running at maximum capacity for 2 million years, throttled back. The mechanism of termination is as instructive as the mechanism of initiation. The Rangelia volcanic system did not switch off abruptly. Large igneous provinces do not operate on human timescales. The eruption rates declined gradually over hundreds of thousands of years, reducing the volcanic carbon dioxide input to the atmosphere incrementally. Simultaneously, the accelerated silicate weathering that the rain itself had driven, consuming atmospheric carbon dioxide in the reaction between carbonic acid and silicate minerals, had been drawing down excess carbon dioxide throughout the wet phase. These two processes, operating in the same direction, produced a slow but inexorable decline in greenhouse forcing. The atmosphere cooled. The saturation vapor pressure dropped. The hydrological cycle contracted toward a new equilibrium. This termination sequence is one of the most compelling demonstrations in the geological record of what Earth scientists call the long-term carbon cycle, the set of geological and geochemical feedbacks that regulate atmospheric carbon dioxide concentration over timescales of millions of years. The silicate weathering feedback is the most important component of this system. It is why, over the billions of years of Earth history, despite episodes of intense volcanism that repeatedly injected large quantities of carbon dioxide into the atmosphere, the planet has never entered a permanent runaway greenhouse state. The rain consumes the carbon dioxide that drives the warming that produces the rain. The system regulates itself, not on human timescales, not on civilizational timescales, but on the deep timescales of geology, where 1 million years is a unit of measurement as routine as a decade. The world that stabilized after the Carnian pluvial episode was measurably different from the world that had preceded it. The difference was not merely biological, not merely a reshuffling of which animals and plants occupied which ecological roles. It was structural. The continental surfaces had been physically reshaped by 2 million years of accelerated erosion and sediment transport. Mountain ranges had been lowered. River deltas had been built. Coastlines had been reorganized by the deposition of enormous sediment wedges at continental margins. The chemistry of the ocean had shifted, with new carbonate producers, the scleractinian corals and their associated reef communities, beginning to rebuild shallow marine carbonate systems on a foundation of different mineralogy and different ecological organization than the sponge microbial systems they replaced. The dinosaurs that inherited this restructured world were not, in the immediate aftermath of the Carnian wet phase, the dominant megafauna of the planet. That process of ecological ascent took additional millions of years, extending through the Nourian and Rhaetian stages of the late Triassic and culminating in the end Triassic extinction event approximately 201 million years ago. A separate crisis caused by the eruption of the Central Atlantic Magmatic Province, which eliminated the remaining non-dinosaurian archosaurs and cleared the final ecological obstacles to dinosaurian dominance. But the foundation for that eventual dominance, the initial radiation, the diversification across multiple body plans and feeding strategies, the establishment of dinosaurian lineages on multiple continents, was laid during and immediately after the Carnian crisis. The rain opened the door. The end Triassic event knocked down the remaining walls. The mammalian lineage that would eventually produce every living mammal on Earth today, including the species reading and writing these words, was also present in the post-Carnian Triassic world. The earliest true mammals, distinguished from their cynodont ancestors by specific features of the jaw joint and middle ear bones, appear in the fossil record in the Nourian stage, immediately following the Carnian. They were small. Almost all early mammals were small, mouse-sized to rat-sized, mostly insectivorous or omnivorous, almost certainly nocturnal based on the relatively large eye sockets preserved in their skulls. They were, in ecological terms, utterly marginal. Prey items for the small and medium-sized theropod dinosaurs that were already diversifying across Laurasian and Gondwanan landmasses. Background fauna, statistically invisible in most fossil assemblages dominated by larger reptiles. They persisted. For 160 million years, through the entire reign of the non-avian dinosaurs, through climate fluctuations and sea level changes and multiple extinction events of varying severity, the mammalian lineage persisted, small, nocturnal, ecologically marginal, but continuous. The physiological innovations that eventually allowed mammals to diversify explosively after the end Cretaceous extinction, endothermy, the derived mammalian neocortex, placental reproduction, the differentiated dentition that allows mammals to process an enormous range of food types, were refined in the darkness of the Mesozoic, in the ecological space that the dinosaurs left available. The rain that opened the world to the dinosaurs also, incidentally and without intention, opened it to the ancestors of every mammal alive today. The modern world carries the Carnian pluvial episode in its structure in ways that are direct and measurable. Every coral reef, the Great Barrier Reef stretching 2,300 kilometers along the northeastern coast of Australia, the Mesoamerican Barrier Reef running along the Caribbean coast of Central America, the coral atolls of the Maldives rising only a meter or two above sea level, is the biological legacy of the scleractinian coral radiation that the Carnian carbonate crisis enabled. The ecological vacancy created by the collapse of Triassic sponge microbial reef systems was the opening that allowed scleractinian corals to establish their 200 million year dominance of shallow marine carbonate environments. Without the Carnian disruption, the reef ecosystems of the modern ocean would almost certainly be organized around entirely different groups of organisms, with different ecological structures and different evolutionary histories. The birds overhead carry it too. Every bird, the albatross riding southern ocean winds over thousands of kilometers of open water, the hummingbird suspended in front of a flower with its wings beating 80 times per second, the emperor penguin standing motionless on Antarctic ice through polar winter, is a living dinosaur. The theropod dinosaurs that began their radiation in the Carnian-Norian transition, diversifying into the ecological space cleared by the wet phase and the subsequent Triassic crises, gave rise to the avian lineage in the Jurassic. The Carnian rain is encoded in every feather, in every hollow bird bone, in every avian lung's air sac system. Anatomical features whose evolutionary origins trace back to the theropod radiation that the disruption of the Triassic biosphere enabled. The crocodilians in every tropical river, the Nile crocodile wading in the shallows of the Mara River, the saltwater crocodile in the mangrove systems of northern Australia, the gharial in the rivers of the Indian subcontinent, represent the surviving lineage of the crurotarsal archosaurs that dominated the Triassic before the Carnian crisis. They did not go extinct. They survived, reduced in diversity and ecological scope, and persisted to the present as the sister group of the archosaur lineage that produced the dinosaurs and birds. Their presence today is a reminder that the Carnian crisis was not a total extinction. It was a restructuring. Severe, prolonged, ecologically transformative, but not terminal. Life does not require stability. It requires only time and opportunity. The oxygen we breathe carries a connection to this event that operates through the most fundamental biogeochemical cycles on Earth. The burial of organic carbon in marine sediments during the Carnian wet phase, driven by the elevated productivity and anoxic bottom water conditions that characterized shallow Carnian seas, removed carbon from the active carbon cycle and transferred it to the geological reservoir. Organic carbon burial is one of the primary mechanisms by which atmospheric oxygen is produced on geological timescales. When organic carbon is buried rather than oxidized, the oxygen that photosynthesis produced to generate that carbon is left behind in the atmosphere. The Carnian carbon burial event was not large enough to produce a measurable oxygen spike on its own, but it was part of the long, complex history of geological carbon cycling that has maintained atmospheric oxygen at levels compatible with complex aerobic life for hundreds of millions of years. The rain fell 232 million years ago. It fell on a world without a single bird, without a single flowering plant, without a single blade of grass. It fell on a Pangean landscape of seed ferns and horsetails and early gymnosperms, on reptiles that no longer exist in any form, on shallow seas filled with organisms whose descendants either diversified into the modern biota or vanished entirely from the record. It fell for 2 million years and it did not stop. And when it finally stopped, The world it left behind was the direct ancestor of the world we inhabit, populated by the lineages it had elevated, structured by the ecological reorganizations it had forced, chemically shaped by 2 million years of accelerated weathering and carbon burial and ocean chemistry perturbation. There is a temptation when confronting events of this scale to reach for the language of intention, to speak of the rain as though it had a purpose, as though the extinction of the rhynchosaurs and the rise of the dinosaurs and the eventual appearance of mammals and birds and the human species were the point of it all. They were not. The rain was a consequence of volcanic degassing. The extinctions were consequences of habitat disruption and food web collapse. The radiations were consequences of ecological vacancy and evolutionary opportunism. The entire chain of causation was blind, thermodynamic, chemical, governed by the same physical laws that operate in every system in the universe, from the interior of a star to the surface of a cooling lava flow to the partial pressure of water vapor in a warming atmosphere. And yet here we are, the species that built the instruments to measure carbon isotope ratios in 200-million-year-old rock. The species that developed radiometric dating techniques precise enough to resolve geological events separated by hundreds of thousands of years within a record 200 million years deep. The species that reconstructed, from chemistry and stone and fossil bone, the story of rain that fell before any mammal existed. Rain that, in the blind and indifferent machinery of planetary geochemistry, cleared the ecological space that would eventually, across geological time, produce the minds now capable of understanding what the rain was. The rock remembers everything. We are only beginning to learn how to read it,